Speaking of, if anyone remote, if you cannot make sense of me, just shout now. I mean, don't shout, like message Christian on Slack. We have moved to a more professional AV setup. Thanks so much to the AV team for squeezing us in. Normally, you're supposed to ask for that like months in advance, and we didn't, and they have come through for us, and so I really appreciate that. Thanks so much. Okay. So today we are going to start talking about requirements, which is this part of our picture, right? Fundamentals of engineering, and it's a fundamental of engineering in general, right? But how does that relate specifically to ML systems versus the problems of requirements in general? Any instructor who ever teaches requirements is required, I think by the Geneva Conventions, to show this comic to illustrate the challenges of requirements. So lest I fall afoul of international law, I have done the same. Right? The whole thing about requirements is that they can be a bit squishy, right? And there's for many number of reasons that this is true. One of them is human language and a set of human assumptions and how difficult it is for humans to communicate. But I'm sure that, especially those of you who have any kind of professional experience, you've encountered something related to these challenges, right? Figuring out what you want to build and whether you've built it successfully, right? Those are some of the hardest parts of building any system, whether there's ML involved or not. So for completeness, because again, teaching requirements and are constitutionally required, we tend to distinguish, or one way to distinguish between different types of requirements is between what we call behavioral or functional requirements. Those describe what the system shall do, right? What it's supposed to do, sort of the specification, what do you want it to do? Whereas the quality requirements, also sometimes called non-functional requirements, talk about other properties related to the provision of those pieces of functionality. Don't tend to like calling them non-functional requirements because they sound kind of unimportant that way, right? Whereas the quality requirements are sometimes even more important than the functional requirements in some respects. And sometimes they can bleed into each other. So this division is a little artificial, right? If your system does compute the square root of the number, but it takes 10 years to do it, right? Is it satisfying its functional requirements, really? Right? It's not that critical, but we do sometimes, when eliciting requirements, have different strategies for each of these, and certainly in the way we express them, it can be a bit different. But it can be helpful to frame things in terms of what the system's sort of supposed to do, like sort of basic functionality features, and the quality with which it's required to do it. One of the challenges here is that, well, it's challenges in general, is that if you ask a customer, what do you want, they will say everything, right? And narrowing it down can be tricky, but some of the strategies here will be different, right? So if you say, hey, do you care about security or scalability, right? Everyone says, well, yes. And so some of the strategies there for helping people make the trade-offs can be a little different depending on whether you're talking about sort of standard features versus sort of the quality with which it's provided, which can be contextual to the domain. And this is the part where I emphasize to you how important this is. I don't want to say nobody. I hate to open this as being like everybody dislikes requirements, because that's not true. There are people who like requirements. There are people who study requirements in an academic sense and get really into it, right? But a lot of the times, I think many of us are engineers and we are tinkerers, and we don't really want to stop and write a bunch of stuff down first. You kind of want to start building, right? And exploratory prototyping and programming is a valid way, actually, to elicit requirements. But I still need to stop and emphasize how important it is to figure out what exactly it is you're trying to build. This quotation dates back to the 70s in the Mythical Man Month, one of the sort of canonical books about the challenges of software engineering, where a lot of the lessons drawn still resonate to this day. I mean, he was talking about the IBM 360 project in the 60s, which shipped years late and full of bugs, right? And all of the lessons that were derived about the challenges of software from that project. But I think all of them are still true, right? And this one is a big one. And over the decades, people revisit this idea of how important requirements are and how difficult and expensive it is to correct problems that were introduced at requirements elicitation time. If you start building the wrong thing, right, that kind of assumption being baked in ends up being one of the most difficult things to correct. So this holds now, right? It's not the 60s anymore. Decade and a half ago, Most of the failures in dependable systems, an investigation from the National Research Council found, are due to poor understanding of requirements or usability issues, much more than sort of standard bugs in code. So this is the part where I tell you, feels like busy work, but it's actually important. It ends up being really expensive late. This is a kind of chart that keeps getting revisited once a decade, right? If you build the wrong system, it's really hard to fix. So please stop and think before coding. That is the point of this module, and in fact, the first assignment. Okay? So we have a few parts to this. The first part of this lecture will be about articulating requirements in terms of setting and, in some respects, untangling the various goals of the system, figuring out what they should be and in what way they support one another or are in conflict. So step one, we want to start by understanding the requirements of the system and its components. So requirement, the system, what it's supposed to do, whether it will be successful, right? What is a successful system in this context? And one way of thinking about this is decomposing the goals of the system, right? These are the goals we want to achieve. If we achieve these goals, we are successful. And it's worth reflecting on the fact that in a system, these are basically layered, right? We can have goals at different levels of the system, and that helps us think about what we are doing at particular parts of implementation or validation or verification, right? So at the very high level, there are the organizational objectives. Those are the innate overall goals of the organization that wants the software. These are basically business goals, right, or nonprofit goals. They're not really usually technical. Something like, hey, I would like to make money by selling you something, right? Maybe I'm going to sell you the service that this software enables. Or maybe if I'm nonprofit, I have a particular mission, right? I would like to reduce hunger in a way that's enabled by this technology, right? That's what the organization that is commissioning or building the software is aiming to do. How do we know that we are achieving those goals? Well, there are some long-term measures that the organization can use to figure out how they're doing. That's a business problem. But often there are leading indicators that are short-term proxies for long-term measures that we will use to evaluate system success in sort of a long-term deployment context, right? So you can't always wait for something like stock price, right? If that's your goal as a business, to move to see if you're doing a good job. In general, you're going to use things that are shorter term, things like shorter term proxies or shorter term indicators for whether the system is supporting the long-term goals. And we'll talk about some of these concretely in a minute. I'm just going to start by stepping through all of them, right? Then there are the system goals, the things we start to care about in this class, right? The goals of the software system, product, or feature to be built. What is the thing that we are building? What is the purpose of that? It should be connected in some way to the business goals, right? We're not building it for no reason. And hopefully there's some way we can look at its behavior or measure something about it to see if it's being supportive of those long-term goals. There's then the user goals, right? The user outcomes, which is a different perspective, right? That is how well the system is serving its users from the user's perspective. These are not always the same. Can anyone think of an example? I'm not saying that a business is always at odds with its users, right? But the user being happy and the business or the system being successful, those are not always the same. Yeah.
Too many ads.
Too many ads, right? So I'm going to riff on this for a second because it's actually a really good example. So if we think about machine learning for ads quality, right, or ads placement, when you do a search with your favorite search engine, it's going to show you ads. Or if you're going to go to a web page, it's going to show you a bunch of ads, right? It is entirely possible to maximize ad revenue and maximize click-through on ads by just putting so many ads that you cannot get to the content, right? In the short term, this will maximize revenue, but it's not meeting the user goals, and possibly in the long term, right, it's going to end up being a problem. So you can see here's a place that goals, both short and long term, can conflict, and user goals may conflict with various indicators of success. Something to add?
I was going to say also privacy and data collection.
So there's another goal that a user might care about, like privacy and data collection. Can we talk about what kind of specific system goal that could conflict with? I can come up with some, but it was your idea. So
I guess from like an ads perspective, I guess like finding like behavioral qualities that would match like user with like the most appropriate ads.
Oh, right. So maybe the system goal is to give the user the ads that are most beneficial to them, right? And the way to achieve that would be to collect just a tremendous amount of data, right? To the point that the user would be uncomfortable, right? That we'd have to compromise user privacy entirely. But we do a really good job on the ads placement, right? I think that's a nice one because it actually system goal is to show you good ads, right? And it could do a better job, but the users are not going to be happy, right? And then, so the last goals are the model properties, right? Those are the quality of the model used in the system from the model perspective. So this is the thing that those of you who like to train the models and evaluate them, those are the kinds of things you care about, right? Accuracy. How often the users click on the ad, right? Or not even, how often the ad is directly relevant, which I guess you would measure by proxy, by how often they click through, right? Accuracy, we'll talk about these over the course of the semester. So let's be concrete. We opened with music generation, right? Suno. So what's an organizational goal of Suno? Why do these people exist? This is not a trick question, but it is an easy one. They want to make money. They want to make money, presumably by selling subscriptions or credits to this, right? Okay. What are some leading indicators about whether they're making money? Something quite short term.
Daily active users.
Daily active users. That might be a decent leading indicator. That's something we can measure very quickly. How well it tracked with the organizational goal is an interesting question. I mean, Christian and I have used that case study in this class every semester for a few years, and I have never paid them a dime. But maybe there's some better conversion that I'm missing. Yeah? Subscribers. I would actually say that subscribers are decent. So maybe daily active subscribers, people who are paying, right? Because maybe you buy 10 credits and then you like peace out and you never come back, right? But there are a bunch of things we could measure here for sure. What are the system goals? The system goals that we're building, the thing that generates the music. So that's a system goal, right? Generate music with some reasonable cost. It builds a constraint into maybe the larger system goal. Yeah.
Follow user instructions. So if it asks for a specific genre, it would provide the genre of the task.
Right. So we're talking a bit here about like the functional stuff, right? We want it to like generate music that is satisfying the user request, right? If we pick Chicago blues, the music should do something in the style of Chicago blues. We're speaking here a bit more about what it actually does, right? The goal of the system is to generate music in response to the user prompt. Maybe it's to generate good music. I'm not sure. What are our user goals?
Create music on their own and give them.
Yeah, you've got some creative goal, right? Create music of your own in response to some. I have a number of athletic skills. Throwing is not one of them. I'm sorry. But it's good. It makes everyone pay attention. You pay attention if you want it. You want to pay attention to make sure that you don't get... If I will inevitably, like, awkwardly hit someone in the head with a piece of chocolate at some point this semester. I'm really, really sorry in advance. I will apologize profusely when it happens, but I'm also apologizing now because I really mean it. I feel really bad about this. It hasn't even happened yet, but it will. User goals. We want to generate some music, right? We want to generate some cool music. We want to
Be able to use the software without encountering any sudden.
Yeah, like we want to use the thing. We want it to not be annoying, right? Not a billion ads. We don't want to accidentally pay them $100 we didn't mean to.
Give feedback.
Do you want to give feedback?
Yeah, to
So we would like maybe the system to be responsive to feedback as a user. Actually, that's often true in developer tools as well, that a lot of times users don't even care if the thing that it gives me is good, but we do care about feeling like we can give the system feedback to make it better, right? So maybe that's sort of an auxiliary goal. We want to be able to generate content, and if it's bad, we want to feel like we can make it better. Otherwise, we'll be frustrated and we'll leave, right? So what are the model goals?
Low inference time.
Low inference time, okay, true. What's a more direct model goal? Low inference time for what?
Realistic sound.
We would like the realistic sound. That is hard to measure. The model should generate realistic sound. Hopefully there's a metric there, right? You're building, okay, you're all machine learning, half of you are machine learning people. I say, train me a model that makes music. What are you measuring?
Good accuracy.
Good accuracy, right? With respect to something, right? It should be accurate. Should accurately make music. I genuinely don't know what the sort of best practice metrics are for music generation accuracy. I'm sorry, I should. But the point is that we've got different levels here, right? Like model accuracy, accurately make music, right? Relative to like make money, right? These are different things. And there are ways in which they're connected, but also ways in which they're not. And in fact, a lot of times they're at different levels, they support one another, right? So if we think about this example of automatic transcription, right? The model goal is to accurately transcribe the text, right? That is also the system goal, right? To give you useful transcriptions, right? A lot of, I'm saying there's different levels, but they're like often pretty related. It's not crazy. We could do a little more of this, but I actually think, we'll do this and then we'll do the case study. Sometimes the model and the system goal are not nearly as related as you might expect. One of the readings we didn't give you for today, but I think is actually a pretty interesting reading, is 150 Successful Machine Learning Models, 6 Lessons Learned at Booking.com. It's from 2019, so it's Paleolithic in age in terms of machine learning literature, but it's really, really interesting in a bunch of ways. This, I think, is the most interesting figure in the paper. What it's showing is the relationship between model performance and deployment performance. Okay, so they have offline metrics, they're measuring model accuracy, and then they have online metrics, right, like how often you actually go and book on Booking.com. What is the pattern that is shown in this figure? Statistically. Yeah?
Better models don't do higher conversion rates.
Right. Better models are not leading to higher converging rates. It was sort of a trick question because it's like, what is this? What are the relationships? None, right? Like, it looks like a random scatter plot because there's no relationship between the offline metrics and the online metrics. And so even though these models they were finding were doing very, very well, when they would deploy them, it wouldn't actually lead to better conversion. The paper posits a whole bunch of theories about this. My favorite one is that really good models can have a bit of an uncanny valley effect, like it freaks people out. If you're like, oh, I had half a conversation about the fact that I'm going to Zurich next week, and then all of a sudden Booking.com is like, hey, book a hotel in Zurich. I'm like, what? Right, freaks me out. I'm not going to click on it. There were other theories, but that's one I like, that actually maybe a less reliable model is more in line with the user goals and will lead to better system and overall business performance, right? There are a bunch of theories like that. There are a bunch of other takeaways, right? Business value requires actual testing. You need good metrics in practice. Model performance is not everything. So I will lead you a little bit on this. Goals may also explicitly conflict with one another. So that was an example where they didn't support one another, right? One was not really related to the other. Here is one where ultimately I think you see that goals were in conflict with one another. So we did have you read a paper called Making Data Science Systems Work, and we told you to focus on the self-help legal chatbot for today. It's actually quite a good sort of sociological study of data science systems and what makes them effective. So I want us to talk about what the goals for the self-help chatbot were at the different levels so that we can have a discussion about it. So that will be our breakout. We want organizational goal, leading indicator for it, product goal or system goal, user goals for multiple users. There are multiple users in this context, and a model goal. And then if you're done all that and you're still talking, right, talk about whether and to what extent these support or are in conflict with one another. You should be able to find the paper on wherever these things are linked right now. I'm sure some of you are pulling up Claude to summarize it in a panic, and that's fine. Please have a discussion about goals and put them on Slack. We'll have about 8-ish minutes, and then we'll come back together. All right, so what's going on with the chatbot? I will start by saying, I looked quickly at some of the answers. I will say I think some of you are overthinking model goals a little bit, right? Like you're building a model. How are you built? Like, overthinking it. Not everybody is, and I didn't see any like outright false answers, but I think you may be putting too much thought into it, honestly. So I don't have any chocolate, so now no one has incentive. I love how much drama there is in this room to like up and down. Someone tell me goals. What's the deal with this chatbot? Say true facts to me about this chatbot. I love this all the way, all my stuff today.
We eventually want to convert the users of the chatbots into paid customers.
Right. So, keep going.
That will result in a bigger customer base and more revenue.
Right. So the organizational goal, they are trying to make money, right? And maybe I'll put words in your mouth. A leading indicator might be user conversion, right? They have someone chatting. How many of those are they successfully handing off to the lawyers that they're trying to serve with this chatbot, okay? So the product goal then is what? What's the goal of this system?
To provide accurate legal information.
Right, so the product goal is, the users are going to ask it some questions, and it's supposed to like provide them legal information that is correct, hopefully. And if not possible, hand them off to some lawyers, right? Real lawyers, right? That's an important part of the product. It's related to the organizational goal. But the system is supposed to provide accurate answers to systems. What are the users' goals here? Yeah, get legal advice, right? I have a legal question. I'm going to ask this chatbot. Hopefully it will help me. I'm not going to ask a chatbot for legal advice myself. I'm too skeptical, but that's the user's goal in the system. They're going to go to the chatbot. Okay? Well, they're one user of this system, though, right? They're not the only user of this system. Who are the other users?
The law company?
The law companies, right? So the law companies are also using it, not in the direct way. The law companies aren't asking it for legal advice, at least not as of when this was written. But they're using it because they're trying to get leads. What's the model goal? Now you'll know the good way to avoid getting the microphone is to avoid the aisles.
Lead and guide the conversation in the most natural way as a human.
Right, so there's a little bit of stuff going on here with the model, right? One is that the model here is trying to, sort of in this older generation chatbot, right? It's trying to redirect the human into like the pattern that the chatbot can handle, right? And it's trying to do this kind of naturally, right? So, but it's still fundamentally a machine learning system, right? So it's trying to do this with respect to some training, right? There's some accuracy entailed, right? It's supposed to accurately and naturally, according to some metric, redirect the human so that the chat can do its job, right? And I said when I introduced this breakout, well, I didn't say it, but I certainly implied it, but I've lost my, goals may be in conflict with one another, right? Read my mind. Why did I say that? You can shout.
I guess sometimes like certain factors or certain goals would almost counteract each other, such as maybe latency. If you want a fast response, that could interfere with a well thought out.
Right. So there are some natural ways in which speed might be at odds with accuracy, right? That's one possibility. What else?
So if all the users come to the chatbot and get all the free legal advice, that's really good, then they wouldn't go to a law firm, and that's not what the law firm wants.
Right. And so I think there's an explicit quotation that I may even have on a slide, so let me go see. Right? The user goal is to get good legal advice. The model goal is to be accurate in its ultimately legal advice, right? That's not the goal of either the lawyers using the system or the company paying for the model, right? Their goal is to get people to pay human lawyers, which is almost explicitly at odds with the goal of the data scientists, right? Which is to make a good legal chatbot. Which is one reason I like this in some respect, right, as an example. Because the data scientists kept saying, well, the chatbot's really not very good. It's not handling edge cases very well, right? The director of technology of the company said, look, 80% success of the chatbot is sufficient, right? It's good enough for people to come to the chatbot at all. But if it did a perfect job, then we wouldn't actually get any paying customers. So what we actually want is an 80-20 kind of system, right? The data scientists, like, I want a perfect system. They're like, no, please don't build a perfect system because we're not making money on that, right? Because of the service that they are providing, which is the service to the lawyers, right? Which is direct clients to them, which is effectively what this is saying, right? Let us get you a lawyer. That's what we wanted in the first place, right? We wanted the chatbot to create leads. That's the leading indicator, because that's what they're selling. They're not selling the chatbot per se. So it's a place where, you know, it's meaningful to break down the goals, to know what you're evaluating, what the requirements are. But at the different levels, the goals are in often contention, right? That making the chatbot too good would be bad, actually. So in this sense, more accurate predictions may not be that important. And this is true a lot of times, right? Not just in this explicit context, where if they did too good of a job, they would cannibalize their actual market, but in the answer we got before, right? If it takes too long, or if it's too expensive, if inference is too expensive, then it's not actually a win to make it more accurate. When large language models first started to get shoved into everything, right? It's a bit of a question. If you're using large language models for inference for ad selection, right, in an ad prediction model, it's expensive to do inference that way. Are you making enough money per click to make it worth it, even if it is more accurate, right? Those kinds of, the quality requirements can be at odds with the system or behavioral requirements, or even the model requirements, the thing that we're trying to optimize for. You can always make the model better. Yes?
But in that chatbot, if the accuracy, if it's too accurate, then it's not, how should I put it? Isn't it a problem of the requirements of the model that, you know, the ultimate goal is to make the user go to receive human legal advice? Because you can say to a programmer like, hey, I want you to give me an app that gives me legal advice, but not like too perfect. But then probably the problem is with the requirement. You should probably ask the programmer to do a legal chatbot that the ultimate goal is to make that legal rather than legal advice person.
Right. So the point you're making is maybe this is a problem with the requirements. And I think that because maybe what the requirements should have been was make a chatbot that's 80% accurate, right, explicitly. But I think what you're identifying is actually sort of the communications problem that's really core in requirements elicitation, right? And why it can be helpful to decompose goals in this way so that you actually understand what's going on. Because if I came to you and said, hey, I want to build a legal system chatbot, and like when it gets too complicated, I want to find, you know, I want to put them in charge of lawyers. Right? You're like, oh, okay, so you're going to do your best, right? Because that's what we do as software engineers and as data scientists. And it's not until we get down into it where we're like, wait, actually, I don't want it to be 100% accurate because the inference is too expensive and I actually want some leads, right? So yes, it is a requirements problem, but it's a requirements elicitation and expression problem. I don't think it was like people were trying to be confusing. You know what I'm saying? It's just that people are confusing. And so like confusion happened, right? So it's a very human story actually, which I think is true of most of software and requirements. And especially here where it's like, I think they didn't realize what the requirements were until they end up having these discussions about it. Because if you're the CTO, you're thinking like at one set of problems, right? And if you're the data scientist, you're thinking about another. So that's why I think it's an interesting case study in that respect. Okay. So that's one way to think about requirements and goals and the way they can be in tension. One part of the next assignment will have you decompose goals in this way. Another way of thinking about systems and what they should do is in terms of what they shouldn't do, right? Last week we talked about risks, a lot of the risks in systems. And there are ways in which the failures of ML-based systems can be different than failures in non-ML-based systems, but that also are not specific to ML. I'll give you some examples. And then we're getting to a point about requirements here, actually, and about the way things fail. But let's first talk about some failures. So this is an ATM, a facial recognition system deployed that, by all accounts, the facial recognition worked well. Anybody saw this when it happened? It's a few years back now. This person is being held up, basically, to the facial recognition system on the ATM. So I would say there was a failure in this system, right? The system failed. I don't know if we can blame the facial recognition part of it, though, right? Even though the machine learning is fundamental to this, right, for this to work, for this ATM, right, you can't blame the ML for this, right? There's something else about the way it was integrated into the system that led to this failure. And I would say it is a failure, right? It's failing to support everybody's goals. Presumably the bank wants people to log in accurately, and the person wants to log in accurately. Like, all of our organizational system goals are all aligned, right? And still there is a failure. There are other things that are more, let's say, specific to machine learning types of failures. So a number of years back, there was quite a bit of coverage of Amazon scrapping a secret AI recruiting tool. It's all come back now, right? But there was quite a bit of press on this because it ended up being biased against women. So what's the root cause? Like, what happened? Like, what's the issue here?
The data was skewed towards men, so the AI the answer was biased.
Yeah, so we're going to have whole lectures about bias, right? But the basic issue is that the data in tech, right, tech hiring, it tends to be very male heavy, right? And so for various reasons, the data was biased, and so the model ended up biased, right? You could end up making a fairly accurate predictor if you just key on gender, right, when it comes to hiring in tech, not because one gender is necessarily better than the other, but because one, there's a lot more of one of them than the other, right? Like, if you're just keying on accuracy, right, like numbers, if the distribution is biased and you're not careful, you end up with a dumb predictor, right? Even if you're doing smarter machine learning than that, it can still happen. There's lots of things like this. Here's a different one. So that's a model problem, right? That's a model training problem. So we think about this. This is a sort of system integration problem, right? A failure to think about sort of physical reality. This is a model training data bias problem. Here's a different problem. So here's an issue where Tesla autopilots led cops on a high-speed chase because the driver was totally passed out. Tesla has a system where it's checking if the driver's hands are on the wheel, right? Because you're not supposed to just like get drunk and go to sleep and have your Tesla drive you home. You're supposed to be in control of the vehicle at all times, and that's how Tesla says it's not their problem because the driver's always paying attention. So something went awry. What happened? What's the root cause here? Yeah.
The driver's negligent.
So the driver is negligent in some way. We can blame the driver. I'm happy to do that.
The system could be exploited to allow negligence.
Right, the system was imperfect in that it did not prevent that negligence in some key way as well, right? Both the human wanted to find a loophole and the system did not prevent that loophole meaningfully, right? Now, again, we can start making engineering trade-offs here, right? There are lots of trade-offs. How else could they do it? Well, okay, they could also have a camera watching you, checking your eye focus, right? They could also have, I don't know, somebody watching you remotely, making sure that like there are so many things you could do, and at some point you make an engineering decision, and I will absolutely make fun of Tesla so many times this semester because it's one of my favorite hobbies, and it is free. But like, in this respect, like, you know, there comes a point where, like, okay, it's a cop-out, but like, there's an engineering trade-off to be made, right? You could put a whole bunch of other interventions in, but at some point, a human wants to find a loophole, and what happened is a human found a loophole. Here's one that's maybe a little bit, I mean, it's older and a bit interesting. So one of the kind of big not early, but like one of the big inflection points in statistical machine learning getting a lot of popular press was Watson. Anybody tell me, or remember what Watson is? It's probably older than you are at this point. I watched it live, yeah.
I think it won the Jeopardy competition.
It did, it won Jeopardy. So Watson beat Ken Jennings, who was the winningest human of all times. And I forget, everyone forgets the other guy, including me. I feel bad about that, because like, he's important too. It did very well, it won Jeopardy. There are a couple of things about it that are funny, actually. The first is that it actually lost the final Jeopardy question in pretty spectacular fashion. It was just like so wrong in a way that was like really weird. The question was about which US airport has the following property or something like that, or which US city has airports named after two World War II heroes. And it says Toronto? Question mark, right? And everyone was like, It didn't bet a lot of money because it knew it was uncertain, and so it won anyway. It was one of those moments of like, yeah, machine learning is good, but also it's weird the way it fails. But that's not the failure I want to talk about right now, actually. The big thing IBM was talking about was like, this isn't just a trick, right? It's not just for Jeopardy. It's going to revolutionize healthcare. And that's what they tried to pivot it into, was basically diagnostics and better support for doctors and stuff like that. It's going to, take on cancer, Watson's next feat. The computer brain is training alongside doctors to do what they can't, right? This was all the press. This was like 2009, right? And it just didn't work, right? It just didn't work. We got concerns from them that the recommendations it was giving were just not relevant. It would suggest a particular kind of treatment that wasn't available in the locality in which it was making the recommendation, or it didn't square with the treatment protocols in use at the local institution, and so on. So this is a sort of interesting kind of failure that's both model and system in some respect, right? Like, it's not being sufficiently accurate with respect to context in some way. And so if you think about the different kinds of root causes of these different failures, right? Some of them are the model, and some of them are very much not. And a lot of them have to do really with the environment, fundamentally, that whatever it is operating in, right? It has to do with when it's deployed, what is it interacting with, and how does that impact basically utility, right? Because here it's interacting with a person who's just shorter than the system assumed. Here it's interacting with a world where training data versus actual data don't align very well. This is operating in a world where humans like to trick systems that they find inconvenient. And this is operating in a world where context really, 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 really matters in healthcare, and not so much in Jeopardy, actually, right? That's the whole point, it's just sort of random trivia. And so we're thinking about all of these failures, right? And there are some of these that can be traced a little bit to the models. Maybe we could make Jeopardy better, not Jeopardy, Watson better. But in a lot of them, that's not the case, right? A lot of these failures are not really directly traceable to the model, and making the model better would not solve the problem, right? Because the problem has nothing to do with the model fundamentally. So this goes back to our original framing of this problem, which is that we're talking about machine learning as a component within a system. And we need to understand other parts of that system and the environment. And a lot of times, sort of the worst failures occur due to misunderstandings of the environment or the system's place within it. So this is where we get really pedantic for a minute about requirements. We used to actually have the class read this paper. It's called The World versus the Machine. It's really academic in its treatment. I actually think it's a really interesting way of thinking about software and its failures. Maybe not to the point that it makes sense to have you all read it at this point, but I would like to cover some of the basics because I think it's a nice way of understanding the different parts of requirements and how they can, when well expressed, help us understand and prevent certain types of failures. So the key idea here is that software exists in the world, right? Software exists for some purpose, right? There is some system goal, okay? It does that by taking inputs from somewhere, maybe from other systems, maybe from sensors, maybe from humans, and producing some output that goes to some kind of display or actuator or something, right? And through those ways, it is interacting in some way with the real world, right? A system is only interesting or meeting its goals if it has some effect on the real world, right? And you can think of that in the classic, like, cyber-physical system way, like an autopilot takes inputs from sensors, it then converts that input into prediction, it turns those predictions into signals to actuators to like move the steering wheel, right? And then the car moves in some way. But this framing is true of any software, right? So like Google Slides got input from me via typing and stuff, right? It's now affecting you because it has sent the things on the screen to the screen and you are taking it in via your eyes, right? If it couldn't send out the data into the world in some way, it would not be accomplishing its goals, right? It accomplishes its goals by producing output that interacts with the world in some way, where the world in this case is you, right? This is true of any software system. A requirement for a software system describes the desired state of the world, right? It describes the effect we want to have on actual reality. Software is trying to affect that by sensing and manipulating the environment into this desired state, right? So when you're making an expression about what a system shall do, it shall be in terms of things that happen in the world, not things that happen inside the software. We don't care about how the software does it necessarily. We care about what it does. So this is a place where we can distinguish between a requirement and a specification, right? It's a bit of a terminology thing, but I think breaking it down this way can be instructive. The system requirement is what the system must ensure in terms of the desired effects on the environment. The software specification is what the software should do, expressed over the inputs and outputs that it's using to interact with the environment. So I'll give you some examples to concretize it for a second before I get to how this leads to software failures, because it's relevant. So imagine that we would like to have a smartwatch-based fall detection and emergency response system, right? My watch does this, except I turned it off because every time I went to a trampoline park with my kids, it tried to call 911. It has some kind of model. There's like a gyro something, and it detects when you move too fast and stop suddenly, and then it offers to issue emergency response, right? So the desired effect of this system on the world, right, is we would like the system shall initiate an emergency call when the user has fallen in a dangerous way, right? That's about the world, okay? How does it do that? What are the inputs and the outputs? Well, the inputs are the gyro that detects that I've fallen or jumped too enthusiastically, right? The outputs are things like notifications that buzz, right? That's an actuator. It causes my watch to buzz. Maybe it can be automatically given the ability to call 911, right? So it has a connection to a system that will call someone, that actuates a human reacting, right? So those are the goals and the requirements in the real world. If we can contrast that with the things we would say about the software, right? The software specification to implement that, right? That's a different thing. That's something like some model receives data input from the sensors. When the model output is greater than whatever threshold, then issue call to function that calls 911, right? There, the output actuator is the call to function that calls 911. The input is the input from the gyro sensors or the model or whatever, right? The specification for the code that you are writing is in terms of the inputs it's using to detect the world and the outputs it's using to affect the world. But it's not actually, the specification is not when the software receives input from the model saying the person has fallen, it shall call 911, right? Because it can't do that, because it's not real, right? It is a computer. It can call a function that we understand to call 911, but it can't actually affect the state of the world, right? So I want to talk about shared phenomena, and I want to skip ahead to the slide before I skip back. So the shared phenomena, so there are the things that the software that can detect and the things in the world, right? The stuff in the middle, the software cannot directly satisfy requirements because it relies on assumptions about the environment. And the shared phenomena are basically the things that connect the environment with the software. So for example, we are assuming that when the gyro says some threshold above some number, I have fallen, right? The software doesn't know that I have fallen. This assumption we are making about what that value means, right? That is an assumption. It connects the real world reality of me falling to the thing that the software is trying to reason about. So the key thing in requirements is to make those assumptions explicit, because they bridge the gap between what we want the system to actually do and what we say that the software is supposed to do when it's implementing. It's formally we say, okay, so this is like an entails, right? We're trying to say, can the system satisfy its requirements? What we're actually saying is, given the assumptions and the specifications are the requirements, can the requirements be satisfied? So Claire, why are you going on about all this like super academic formulation, like fun trivia, right? But what does that have to do with anything? It has to do with things because often the worst kinds of breakdowns have to do with assumptions, fundamentally. The assumptions that connect what the software is specified to do and what we actually want it to do in the world. A lot of these examples, or I think some of the most instructive examples, come from safety critical systems failures. So often like plane crashes and the like, for a couple of reasons. First, because they tend to be very well studied, right, in terms of figuring out the breakdown. And second, because they are cyber physical. So for example, we will talk about Lufthansa 2904, which was a runway crash. So here's what happened, basically. It was landing, I want to say in Warsaw, and it skidded off the runway because the brakes basically wouldn't turn on. Okay? This was a software problem because it was an Airbus. It was an Airbus prior to 2015. So here's the issue. The reverse thrusters decelerates the plane after landing. The requirement here, note that this is about the world. Reverse thrust is enabled if and only if the plane is on the ground. Okay? Because you absolutely do not want reverse thrust to be turned on if the plane is not on the ground. Right? Like you can understand why that's true. We have all flown in planes. So, most of us have. Okay? So that's a requirement that's about the state of the world. The software specification is that reverse thrust is enabled if and only if the wheel is turning. But the wheel is turning, that's a statement about the world, right? And so we can't actually know that because we're software, we're not real. And so instead, it's expressed in terms of values on sensors. And at this point, this requirement was expressed as follows, right? The wheel is determined to be turning if either 6.3 tons of weight are sensed on each landing gear, or sensors indicate the wheels are turning faster than 72 knots. So there are two assumptions here, right? One is that the wheels are turning if and only if the plane is on the ground. The other is that high amounts of weight are only on both landing gears if the plane is on the ground. That's how we're connecting the sensor values to reality, basically, right? Those are the assumptions that we are making. The problem is that on a really windy, wet day, the plane was wobbling, right? So neither wheel got enough weight on it at any time, and the plane was skidding. So neither wheel was going fast enough to detect those sensors, and so reverse thrust wouldn't engage. And it went off the end of the runway. So here, wheels are failing to turn even though the plane is on the ground, assumptions violating, right? And there wasn't enough weight because of the wind. And there are a lot of examples like this, some of them less dramatic, some of them more dramatic. I could do a whole lecture on the 737 MAX. I'll try and spare you. But the point is that here, this failure, right, it's not really about machine learning, but it's a kind of failure that shows you the importance of assumptions. And then we can get back to the way that connects to the assumptions of a machine learning system, right? When you are trying to articulate your assumptions about a system and the requirements and the specifications about the system, being clear about what the assumptions are can help you identify various elements of risk. Because if you remember those systems we were looking at, the failures were almost all related in some key way to something environmental, some assumption that had been made about the environment. Nobody under 5 foot would ever try and use this thing, right? The user wouldn't get drunk and then try and trick me, right? These are all assumptions that are being made. So let's see if I want to do another one of these examples. I think I do. So let's talk about lane keeping. Let's talk about lane keeping in the slides that will actually update for you and not just for me. Okay, so here's a requirement in lane keeping. The requirement is the vehicle must be prevented from veering out of the lane, right? These are all statements about the world, okay? The software, the goal, the requirement of the system is to prevent the car from veering out of the lane, or the goal is to stay in lane. So that's straightforward enough, I think. let's think about this for a second. If that's the requirement, what is the specification? Now, I skipped a step without saying, okay, how are we getting the sensors? But assume various sensors, right? Like, what's the specification that we could use here? Because this is a more machine learning model kind of thing, right? Or some combination of models, usually, because we tend to. So lane markings, what about them?
Identify the images.
Right, so we're beginning to talk about some of the systems that would be involved here, right? The model shall accurately identify lane markings, okay? I'm still kind of expressing things in terms of world phenomena, though, right? So we're going to have some kind of data set where the markings are known and indicated, right? And we want to say the model shall achieve certain accuracy in identifying lane markings, right, as indicated by the data. But what about live? How shall we prevent this system from veering out of the lane live? What kind of specification could we use there? Well, we need to identify the markings, and then something else needs to happen, right?
It needs to turn within a certain amount of time.
Right. It needs to actuate wheel turning, right? When veering is detected or predicted with respect to identified lane markings, the wheel must be turned. So there's two parts to this, right? One is we have to accurately identify lane markings. The other is we need to influence car trajectory in some period of time. Okay, so this is a different way of saying the same thing. What assumptions are needed? Yeah. We assume that roads are marked with lanes, or have their lanes marked, right? We assume we are working on a road that has lanes. This is a big one, right? That there are lane markings to identify.
And that the middle lane is thinner than the two lanes that are holding the car.
Right, yeah, we're making some assumptions probably about the distance of the lanes as well, right? We're making some basic, and there's reasons that lane assist will like turn off in my car, right? I love lane assist, it's amazing, but like it doesn't work all the time. It's assuming that they're visible. It's assuming they're not covered in snow. What else is it assuming?
There are no other lanes. There are not actually the marked lanes.
Right, there's not other lanes, right? Sometimes like there's been construction and we've got like a new set of lanes. It's like kind of on top of the old set of lanes, and like which lanes?
The driver isn't actually needing to go in the other lane.
Right, so we're making some kind of assumption that the driver is not trying to change lanes on purpose, right? Sometimes when you're veering, you're not veering, you're trying to change lanes. And cars will do different ways of dealing with this assumption, right? Like it'll yell at you if you don't use an indicator.
The wheel is working, the function, like it is working as expected.
Right, so there's an assumption that the wheels basically will respond to the controller commands, that like the actuation will be effective. And this is something that can kind of be checked, right, as they're being issued, is the car trajectory changing, but there's still this core assumption. But you see what I'm saying? Like I am responding to each of these with, you think about the interventions that are happening in the system to deal with these assumptions, right? And when they are violated. Because the model itself can't know, because the model is just making predictions. And instead, we build other interventions into the system to contend with those assumptions explicitly, right? Which is one reason that expressing requirements and specifications in this way, and in terms of assumptions, can be helpful in breaking down risks, or at least knowing where you might fail and why. We'll talk more about that next week and how to prevent those kinds of failures. So here, just to be completist, the shared phenomena is the interface between the environment and the software. So in lane keeping, it's going to be things like LiDAR, if you're not in a Tesla, the camera, the pressure sensors, the GPS. The output will be signals generated and sent to engines or brake control or steering. Software is only influencing the environment through that interface. We can only assume how they will behave. And we can check those assumptions, but we can't actually, do it. So we've made a bunch of assumptions here, right? Some are that sensors are providing accurate information. The steering wheel is functional. And the important bit is that in terms of whether a system is satisfying its requirements, there are three places that this can all go to hell, right? One is impossible or inconsistent requirements, right? Or incorrect requirements. We could say that the system's supposed to do the wrong thing. This happens a lot. But also, we can fail to satisfy them because of missing or incorrect environmental assumptions, right? Maybe it's operating in an environment that we didn't handle. And finally, we can either have the specification that is incorrect, maybe that's not the way the software is supposed to implement the requirement, or that is incorrectly implemented. The last one is the situation I think most people think of. If I say, oh, there's a bug in your code, you're thinking null pointer exception, right? And that is a way that a system can fail to satisfy its requirements. That is a way in which the code incorrectly implements itself with respect to what it's supposed to do, right? It fails to implement the desired specifications. But a lot of, I think, the most complex or interesting system failures, or I think maybe most of them, are more about the assumptions and the requirements than they are about silly programming mistakes that we make, right? Which is one reason I think it's instructive to break down what systems are supposed to do in this way, because it's not just about preventing bugs, right? You do want to do that, but that's not the only thing, in fact, often not the most interesting or difficult thing that can keep a system from being useful to humans, which is what they're supposed to do. Okay. Now, I showed you some examples, and I've talked about examples with the planes, right, that have nothing to do with ML. But there are a number of ML-based system situations that I think are specific to machine learning that can lead to violated assumptions, that can lead to system failure to satisfy requirements that are worth thinking about. So I'm basically going to give you a little bit of a laundry list, and I'm sorry because it's my least favorite kind of lecturing. But we can make assumptions about correctness of model predictions in any number of directions, right? We can assume that offline performance correlates with online performance. We can make assumptions about human behavior and how they interact with the system. There's a whole bunch of interesting examples of this, and we'll see some of them later, especially when we talk about bias. But I think that some of the more interesting ones have to do with the systems that law enforcement or court systems have been using for predictive policing or for predicting recidivism, right? There are these models that municipalities are buying to suggest to the cops where they should go patrol, right? But then there's evidence, sort of sociological evidence, that cops will only take the recommendations when they are consistent with the thing that the cop thinks they should do anyway, right? And it's not specific to cops. Humans are like this, right? So we may assume that the human is going to faithfully listen to what we tell them to do, but humans don't like to listen to what they're told to do when it is not consistent with the thing the human already wants to do. That is a property of humans. And so thinking about that and the way that the humans interact with the system and how the predictions are used and presented is important. We make a bunch of assumptions about training data, namely that it's representative of actual deployment data or online data, right? And that it's meaningful in some way. And we'll make assumptions about stability of data, about reliability of sensors, reliability of human input, right? A lot of times we may be trying to tune to human responses to surveys, for example. So the question is, well, how often do humans agree? I'm having this problem right now. I'm trying to help prototype some software to help us manage an enormous volume of applications to a summer program, right? And I just have incredibly noisy human rater data from previous years. The problem is, how often do we agree with each other? And the answer is maybe not as often as you'd like. And that's another thing. You think about some of these systems that are used for things like recidivism prediction, right? We would like to have less biased sentencing in our courts, right? And you're like, well, okay, I'm really I am genuinely okay, having a machine learning model do this, predict how long someone should go to jail, given how biased models are, I don't feel great about that. But it turns out judges are also tremendously biased, right? So it's picking your poison a little bit, and so you have to think a little bit about the reliability of the human input you're either training on or trying to replace. There are often unrealistic or missing assumptions. A lot of times in cars, a big issue is the effect of weather conditions on sensor accuracy. This happens in planes too. But there's also maybe the more, I don't want to say insidious, but challenging issue that comes up, not just with physical sensors, of concept drift, right? Concept drift being an environment that's shifting over time so that the underlying distribution changes. So for example, like we've been talking about something benign, movie prediction, music prediction, right? How could Suno's needs need to change over time if a new type of music becomes very popular, right? That's sort of what the user maybe has shifted over time because tastes change, for example, right? Then whatever you trained on may no longer be indicative of what your users are looking for, and the model is no longer effective, even though the model itself has not changed. There's been this idea of concept drift. There are also adversaries, malicious actors trying to violate assumptions. There are adversarial attacks on stop signs. There are humans who weight down their steering wheel and get into high-speed chases. I think some of the most interesting ones are feedback loops where the system repeatedly acts on and changes on the environment so that earlier assumptions end up no longer holding. We'll talk about this in later lectures because I think it's one of the more interesting things that are actually pretty specific to a lot of machine learning systems, where basically their outputs become their inputs, and so assumptions no longer hold. So if I can put together a lot of these things. First with a bit more of a laundry list, right? If you want to establish some requirements, it's worth starting to think about what are the environmental entities and what are the software or ML components. What are the desired requirements for the system over the environment? What is the interface between the environment and the software? Identify the assumptions being made to connect the two. Check whether these things hold, right? Rinse, repeat. And I think if we go to revisit, each of these examples, we can hammer this home, but in the interest of time, we're not going to do that. Instead, what we're going to do is, in 2 minutes, I'll talk about gathering and negotiating requirements. And the very, very short answer here is that you actually have to go talk to people, right? Understanding requirements is hard. And it's really the yes, but problem, right? That's what I ask for, but now that I try it, what I really want. So actually I was saying I'm working on trying to develop some software to help us process large volumes of applications. I really time-boxed my effort on this because I predicted what was going to happen perfectly because I'm a genius. I said, I'm going to build this thing, and I'm going to show it to my colleagues, and they're going to hate literally every single thing about it. So better that I prototype it enough for them to tell me all the things that they want instead, and then do that instead of wasting more time. That is 100% what happened. Yes?
What if, the users or clients do know the problem, but have different crazy solutions that might not be efficient? Shouldn't be the goal of the programmer to understand fully the problem and come up with the best solution?
Right, so this is a really good question. The question is, well, what if the user is unrealistic, right? What if the user wants things that are impossible? And a lot of the sort of tension in negotiating requirements comes from the fact that there's no one person that you are trying to satisfy, right? More formally, those entities are known as the stakeholders in the system, right? And stakeholders tend to have different or competing needs, and the goal of the designer, the person establishing the requirements, is to find a way to identify those conflicts and then reconcile them, right? So the one problem is that users may not know what they want. Another problem is that inevitably when you speak to all the stakeholders, you're going to get completely different or conflicting answers, and there needs to be a way to negotiate them, right? So for example, if I had asked the chatbot developers, the data scientists, your goal is what? And it's to make a most accurate chatbot, right? That's sort of explicitly in conflict with the goal of the organization, which is actually not to have the most accurate chatbot, right? At some point, someone needs to make a call. And I don't want to say you can't always make a call in favor of making more money, right? Because what that does is cover all your websites and ads so your users don't come anymore, right? So there's still a question of long-term value. But the point is to surface all of the different competing requirements, identify those conflicts, and then negotiate them. So one way to do this, actually, concretely, is to express things in terms of alternatives, right? So I said at the beginning, with quality requirements, if you ask someone, do you want your system to be secure or performant? They will say yes, right? And so expressing that in terms of, well, if the choice is between this and that, which do you prefer, right? Is a better way to get people to elicit kind of ways to negotiate those goals when they are in conflict. This is only a problem for security versus performance, right? Maybe there's some technical solution that will make something slower. Maybe there's an explicit conflict between them. Or maybe doing them both has to do something with cost, right? And so the question is, at what point is your budget inflection point? And expressing this in terms explicitly of what's better, A or B, can be a way to help tease out what people actually want. So in fact, I'm like anticipating myself, right? You want to start with stakeholders. It's not only the direct customers, right? It's also affected people, owners, and so on. We want to think about like who are all the list of possible stakeholders. You cannot inevitably speak to every human on the planet, but you want to identify sort of the most important ones because those are the ones who help you identify what the goals of the systems are and where the conflicts start to happen, right? I have given you basically at a high level already some of the ways to do this. I think in ML prototyping especially, a very effective mechanism for listing requirements are Wizard of Oz experiments. So-called because like you don't actually have to build out the whole model. You can just like pretend and show a prototype that doesn't actually do the machine learning, right? And just pretends and get people's initial reactions to prototypes. In a machine learning context especially, that can be very useful. So there are a bunch of other ways to do this, things like background studies, things like personas to help organize your thinking. I will not talk about them because I think the high-level principles are fine, and also it is 3:20, so I'll summarize. Requirements state the needs of the stakeholders and are expressed over phenomena in the world. Environmental assumptions are important. Identify stakeholders, interview them, and then resolve conflicts. Thank you so much. See you all on Monday.